All right, so hello everyone. Today we're looking at section 3.9 related rates. All right, so similar to section 4.7 that we did, these also have some step-by-step process that you need to follow in order to be able to solve this uh, related rate problems. Okay, so let's look at the strategy. Obviously, you need to read the problem. So, similar to 4.7, I say read and understand the problem. All right. See if you can draw a diagram. A diagram is always useful because that tells me if you understand the question or not. All right. And then, as usual, introduce notation, so assign your symbols. And then they say express the given information and the required rate in terms of derivatives. All right. For example, if I tell you the rate at which maybe the volume of something is changing, you want to write it as dV/dt also. All right. So give your rates in terms of derivative. Then very important, write an equation that relates the various quantities. So you need this equation, very important. You need to write an equation that relates the various quantities. And then you're going to differentiate. So that equation you have is step 5. You're going to differentiate using chain rule. All right. So here we're going to use chain rule. And we say with respect to t. All right. When I tell you the rate at which something is changing is d dt. All right. So it's going to be with respect to time. And they obviously substitute the given information into the resultant equation and solve for unknown rate. All right. Enough about of this step. Let's do an example so that we go through it step by step. Let's look at this one. All right. I'm sure you saw something like this probably in an assignment or so, something that looks like this. But now they say air is being pumped into a spherical balloon. All right. So always read carefully. Air is being pumped into. All right. So let's assume that was my balloon at so I'll just got this V1, all right? So as the first volume of my balloon, you agree that at time T2, the balloon will look slightly bigger because air is going into, so this will be my V2, all right? And obviously, by the time you hit time T, let's say T equals to 10, your balloon will look much bigger, all right? So that's more or less what is happening, all right? So it is getting big and bigger in size because air is going into. And the rate that they give you, so this 100 centimeters cube per second, is going to be a positive rate. It makes sense, all right? Because the volume is getting bigger, the rate has to be positive. If I rephrase this question and I say that, let's say I change the wording and I say, suppose a spherical balloon is losing air at the rate of s. All right, so everything will happen in the opposite direction. So it will start very big and it's going to get small. And the rate then has to be negative because it's getting smaller with time. But for this specific question, the rate is actually positive. All right. And your unit, so for related rate and optimization problem, I told you before, unit is very important. So look at your unit carefully. The unit is cm cube per second, centimeters cube per second. Centimeters cube, you know, is a unit for volume. Second is a unit for time. Therefore, you know that that information I've given you is just dV dt. All right. So you're very confident that I've given you dV dt. Now I ask you how fast is the radius of the balloon increasing? The word how fast, it means what is the rate at which? All right, so how fast, it means what is the rate at which the radius of the balloon is increasing when the diameter is 50 centimeters. All right, so you must not only find that keyword rate. Once you see stuff like how fast, how quick, you know I'm still asking you for rate. All right. So in this case, what am I asking you for? So this guy, you know, dV dt. I'm asking you for dr dt. So the rate at which the radius is increasing. So it's dr dt. That's what I'm asking you. All right. So once you know this information, then you're good to go. All you need to ask yourself is what is that equation that they need to write? You see? So after writing, drawing a nice diagram, stating the quantities that you know, the quantities that you're looking for, you ask yourself, what is that equation that I need to write that is going to help me to establish a relationship between what I know and what I'm looking for. All right. And the key word here is a spherical balloon. Because we're talking of a spherical balloon, it means you need to tell me what the volume of a sphere is. All right. So spherical balloon means you're talking of a sphere. Therefore, you need to give me the volume of a sphere. Why do you need the volume? Because I gave you a rate there, the rate at which that volume is increasing. So you need to start by telling me what the volume is. All right. So let's go to the solution quickly. All right, so if you look at the solution there, I'll just change the color quickly. So the first thing you notice here is I tell you that the rate dV/dt is 100. So this is positive because the balloon is growing big and bigger in size. All right, and I told you that you need to find the rate at which the radius is changing when the diameter is 50 centimeters. Remember, radius is just half of diameter, so you need the radius to be 25 centimeters. All right, very important. This is what you're looking for. This is a special case where if you don't draw a diagram, I won't really mind because all I needed you to draw is just what I drew before. So you started with something smaller, and it gets bigger, and it gets bigger and bigger. All right, and you can just call this your V1 and V2 and so on. Now, what is that equation that I need? You see that question actually. What is that equation? It's the volume of the sphere, which is 4/3 pi radius cube. Very important, we need to differentiate. We need to find the derivative. We need to differentiate that equation using chain rule. Chain rule says that if you look at this equation closely, V is written in terms of radius. It depends. So volume is a function of radius. But now I'm looking for dV/dt. It means I need chain rule. Indirectly, I'm telling you that the radius is also a function in terms of time. Therefore, dV/dt, we're going to say dV/dr times dr/dt. You always need chain rule when you're solving related rate problems. All right. And in this case, dV/dt, you know already. What is dV/dr? It just means go to this equation, differentiate with respect to r. All right. You just get 4 pi r squared. All right, and then dr/dt is what you're looking for. If you make dr/dt the subject, it just becomes dV/dt divided by 4 pi r squared. And then you're good to go because why? Your radius, you see, we compute the radius at the top. Radius is half of diameter. All right, so you get 25. If you plug in this equation, you just have 100 divided by 4 pi times 25 squared, which is just 1/25 pi centimeters per second. All right, so the radius of the balloon is increasing at the rate of 1/25 pi centimeters per second. All right. Now there's something here that I didn't mention, but it's something that I'm going to draw your attention to. If you notice in this question, your volume is given as cm cube per second. And your diameter was given as 50 centimeters. You see the unit there, there's a mass. Centimeters, yeah, you're dealing with centimeters cube. Now you need to pay attention because what happens if I change this and I give you 50 meters? You see, you need to do a change of units before you can substitute down here. All right. So in this case, there was no need to do any conversion because the units, they're going to match. All right. Centimeters cube is fine. If here you have maybe meters cube for the rate, for the volume, and here I give you centimeters, it means you need to convert centimeters to meters. So your reference is this rate that is given. If the rate is meters cube per second, it means every other unit that you have, if you have centimeters, you need to convert to meters. If it's centimeters cube per second, it means your radius has to be in terms of centimeters. All right. If everyone is happy with that, then let's jump to the second example. So the first one was straightforward. So let's see if it gets more and more exciting. All right, example 2. Example 2 They say a ladder 5 meters long rests against a vertical wall. Right? If I were you, I'll draw a nice diagram. So just get pencil. So if I were you, I'll say, okay, let's say there's my vertical wall, and obviously this is, you can call it ground. And the ladder is typically resting there. So you're going to have something that looks like this. All right. And the total is 5 meters long. So you know what this distance is. It's 5 meters. All right. Let's continue reading. They say, if the bottom of the ladder slides away from the wall at the rate of 1 meters per second. All right. So now the first thing you notice is, so this is the bottom. The bottom is down here. They say it slides away from the wall. So it's going in that direction. And they give you a rate. So if you use your coordinate system, you notice that this is just x, so x direction, and this is just y. So in this case, what they've given you, that 1 meters per second, is just dx dt. All right, very important. So that will just be dx dt. All right, so dx dt is just 1 meters per second. And then they say how fast, so just write it there, just 1 meters per second. All right, and then they ask you how fast. Again, you see what terminology they use. They say how fast. They say what is the rate at which. So, like I said, when they use words like how fast, how quick, how slow, all of this is rate. All right, it's d something. All right. So, how fast is the top of the ladder sliding down? So, in this case, we remember there's a top of the ladder there sliding down means there's a change in y. So we can call these dy dt. All right. So if we call this dy dt, therefore we know exactly that we're given dx dt and we're looking for dy dt. All right. And then they say that this dy dt you're looking for, what value is it going to be when the ladder is 3 meters from the wall? So they've given you some x value when the top of the ladder slides down. All right. So how do we solve this? The first thing you're going to ask yourself is, what equation am I going to write that is going to link the known and the unknown? Clearly, looking at this diagram, it's just a right angle triangle, meaning that I can apply Pythagoras theorem. Pythagoras theorem say x squared plus y squared is just equals to 5 squared, which is 25. All right, there you go. So you have Pythagoras theorem. What's the next thing that I said in the previous example you must do? You need to differentiate all true by applying chain rule. All right, the derivative of x squared, if you apply chain rule, it's just 2x. Remember, x is a function of time, so you're going to say 2x dx dt. All right, and then you ask yourself, what's the derivative of y squared? Again, you're going to have plus 2y dy dt, and the derivative of this will just be 0. All right, let's just go to the solution so that I'll highlight what I'm trying to mention here. So let's see. All right, guys, just excuse me for one. All right, sorry for the interruption. Let's just go straight to the solution. All right, so if we look at the solution, this is a diagram that I was trying to explain earlier. You given dx dt, and you've been asked to look for dy dt. We know the length of the ladder is 5 meters, and we know by Pythagoras theorem we can link the sides. So we can link the adjacent, the opposite, and the hypotenuse, which is the length of the ladder. So x squared plus y squared 25. Now, as usual, for related rate, it's a must. You must apply chain rule. So if you solve a related rate problem, you don't see yourself applying chain rule, it means you're not doing related rates. All right, you're wrong. It's as easy as that. There must be chain rule. And how does chain rule works? You're going to consider x to be a function in terms of time. y to be a function in terms of time. With that idea in mind, it means if you differentiate x, you have to apply chain rule. So you're going to have 2x dx dt. You differentiate y squared, you have 2y dy dt. Look at this. This is a constant. The derivative of a constant is just 0. What are we looking for? We're looking for dy dt. It's minus x over y dx dt. You see there's a minus sign there, and it makes sense because when this ladder slides down in this direction, you agree that this rate here has to be negative, sliding down. All right, the ladder, the top of the ladder will be sliding down. The way sliding down means what? Negative rate. All right, hence the negative sign there. Now ask yourself, what do I know? What don't I know? I know what dx dt is. So in this piece here, I know what dx dt is. What else have been given? They give us x. So they told us that x is 3. See, there's information there. They say x is 3 meters, but they didn't tell us what y is. All right, we don't have a problem because using the same Pythagoras theorem, you can solve for y if you know what x is. So if you plug in x is 3 in this Pythagoras theorem, you solve for y, you just get y to be equals to 4. All right. And once you know that, you plug it in that derivative function, you just have minus 3 over 4. And something you mustn't forget is the unit. Please always put unit. So if you just say dy dt is minus 3 over 4, you don't give me a unit, you're going to lose marks. If you give me the wrong unit, you still lose marks. So always check your unit and make sure that they're correct. So in conclusion, I can say therefore the top of the ladder is sliding down at the rate of 3 over 4 meters per second. So this is me interpreting this result here. You can choose to not write this conclusion here, it's fine. Me looking at this, I know what you said because negative sign means sliding down at a certain rate. All right. Is there any question before we move to the next example? All right, looks like everyone is happy. We only have about 3 more examples. So let's keep going. And the trick with the related rate optimization problem is that you get very comfortable with this depending on how many examples you actually do. All right. The more examples you do, the better you become at tackling this kind of problem. All right. Now let's look at example 3. This is a very exciting one. They say a water tank has the shape of an inverted circular cone. All right, with base radius 2 meters and height 4 meters. So let's go ahead and draw a little sketch of what they're talking about. So inverted means that it's going to look like this. All right, so you have something that typically looks like this. All right, and then they gave you the radius here. So there's a radius there, and they give you the height. All right, so they give you this height here. All right. So the height here, I'll just put the value, the height is 4, and the radius there at the top is 2 meters. And then they say if water is being pumped into the tank, so obviously you are, I don't know, probably putting it from that direction. So you point water into the tank at the rate of 2 meters cube. You see again that cube there tells you there is volume. So I've given you dV dt. All right. So always check your unit. Your unit will guide you on what they're talking about. So 2 meters cube per minute. Meters cube, you know they're talking about volume. And it's going to be positive volume because water is being pumped into the tank. All right. So the tank is not leaking water. Instead, water is being pumped inside the tank. Therefore, it's going to be a positive rate. You're going to get 2 meters cube per minute. Positive. All right. If you make a mistake, and you say -2, for example, then I'm going to subtract max because it means that you didn't read the question carefully. They say find the rate at which the water level is rising. All right, this gives you an idea that, okay, when I'm pouring water inside the tank, there will be some, I'll just draw a little sketch here. Let's assume this is water, just put some dots there. And you agree this water here, there's a radius and there is also a height h, all right? Now, they say find the rate at which the water level is rising. So water level in this case, what are they referring to? Obviously, it's not the radius of the water, it's a height, all right? So they ask you for ds dt, all right? where that h is the height of water in the tank. So find the rate of solution water is rising when the water is 3 meters deep. Right, so this is what you're looking for. And then they tell you that find this when h is equals to 3. You have a diagram, you've labeled it nicely, you've written out the quantities that you're given, you've written the quantity that you're looking for, and the conditions, which is just when h equals to 3. What is the next thing you need to do? It boils down to that equation that I always talk about. Ask yourself, what is that equation that I need to write? That is going to help me find my missing quantity, ds dt. To know what equation you need to write, go back to that initial rate that was given. They gave you dv dt. It means they're talking of change in volume. So you need to tell me what the volume of this cone is, all right? And we know that the volume of a cone is just 1/3 the volume of a cylinder. So volume of a cone is 1/3 volume of a cylinder. And volume of a cylinder is just pi r squared times h. All right, so there's 2 there. There you go, you know volume. But now the trick is this volume is dependent on 2 variables. You see that there's radius and there's height. Ask yourself, I need to be able to eliminate one of these variables, all right? Because if I differentiate, if I find dv dt without eliminating one of the variables, I'll end up with some dr dt, which I don't know. Because I don't know the rate at which the radius of water in the tank is changing. I just know I'm looking for ds dt. So I'm looking for the rate at which the water level is rising. I don't know exactly the rate at which the radius of the water is changing. So I need to try and eliminate variables so that r disappears, all right? How do you do that? We're going to do ratios, all right? We're going to compare the size. So we say that the height, so height of water over height of the can must be directly related to the radius of water over the radius of can. Guys, this is very something really important. You need to remember this ratio, all right? I'm not saying that these numbers will always be fixed, but always remember a ratio. You need ratio when you're dealing with the cone, when you're trying to eliminate one of the variables, all right? So look at the ratio of the height of the water to the height of the entire can, the ratio of the radius of water in the can to the radius of the tank, all right? So if you do that, you notice that your r there will just be equals to, so you get 2h equals to 4r, therefore r there is going to be, dr will just be h over 2. All right. So your r there is h over 2, means that where you see r squared, you can just plug in h over 2. And it's going to be h squared over 4. And you have everything now in terms of a single variable h, which is what you want, because now you can apply your chain rule and then you make dh dt the subject. All right. So you see how easy it is to tackle this problem. Okay, so let's jump to the solution as usual. All right. I'm sure you guys like this diagram better than the one I was drawing earlier. So there is a nice diagram there. That is what you're given. That is what you're looking for. These are just the initial conditions, so the radius and the height of the tank. And then you ask yourself, what equation do I need? It's volume of a cone, which is 1/3 the volume of a cylinder. You use ratios. You see, we need these ratios. And this will help us to find a relationship between R and H. All right. And once you do that, you see, I can completely eliminate one variable. So R disappears and I just have pi over 12 H cubed. All right. What do? You apply this, which is called chain rule. dv dt is dv dh times dh dt. If you do that, you end up with pi over 4 h squared times dh dt, and this is what you're looking for, dh dt. Just make it the subject, all right? And you notice that the only thing you need to know here is h, but they told you h there is 3, all right? So you just plug in 3, you end up with 8 over 9 pi. Very important, you need to give me units. So you see there, the water level is right at the rate of 8 over 9 pi meters per minute. All right. You see, for all these examples I've given you, the units, they match nicely, all right? Because you're looking for ds dt when h equals to 3 meters, all right? And if you notice here, you had meters cubed. So you see, it works out nicely. But be careful, because I can now say what happens when this is 3 centimeters, for example. Everything changes, all right? You need to convert this to meters, all right? Before the answer you get is going to be a valid result, all right? All right, someone, let's read some comments there. I think there have been some couple of comments. Let me start from the top. Okay, from the top, I don't see any comment. From the bottom, you say if we are to leave out the unit in the calculation but use it in the explanation, is it still fine? All right. So if you leave out the unit and then you said you use it in the explanation, well, as long as if you don't say, if you can't write it like this and you write it in word as meters per minute, it's fine. So for this example, someone is saying that what happens if I don't put here meters per minute? All right. So the reason why I left it out here, because look, I mentioned it down here. But like I said, I will not be requiring you guys to. It's not a must that you need to give me this piece here. So you need to state your unit somewhere there already. All right. And please make sure that your unit is correct. You can write it like this, or you can write it in words, meters per minute. You can write it in words. All right. All right, let's keep going. We still have a couple of examples to go through. So please, I hope everybody understood that example. Like I said, is very, very important. For those of you that looked at assignment 2, you understand why I'm saying that example is very, very important. All right, so let's look at the next example. Here is example 4. So this is now where we're going to test your sense of direction. I say car A is traveling west of at 90 kilometers per hour, and then car B is traveling north at 100 kilometers per hour. All right. So let's do a little sketch. But before we do that, I'm just going to remind, for those of you who don't know what north, south, east, and west is, I'll just help you again to remind you. So that is north, south, and that is east, and then that's west. All right. Just in case you forgot it. Okay, car A is traveling west, so it's going to start somewhere there. It's going in that direction. All right, it's going there. And then car B is traveling north, so it's somewhere down there. It's going up. All right. All right, that's the information we have. And then they say both are headed for the intersection of the two roads. So they're heading towards some intersection here. Let's call this C. So this was my car A. This was my car B, and they're heading towards some intersection point where we can quite see. All right, I'll just put arrow to show that is the direction they're going. All right, they say at what rate are the cars approaching each other? All right, do you agree that at some point in time, by the time they get closer and closer to this intersection, the distance between this B and A is going to be really small? All right. So it means that you need to be able to establish what this is, right? This line that joins B and A, the distance between B and A, right? Do you agree that as time goes on, let me imagine that we're somewhere here. Look at what happened. That distance they get really small. You see that? It means that distance between them is getting smaller and smaller with time, right? So the action for the rate at which the cars approach each other when car A is now 60 meters and car B is 80 meters from the intersection. So I'll just draw another little nice diagram here. So we now have car A is a 60, so this is now 60 and this is 80. All right. So you see that here the only unknown we don't know, I'll just call this Z, right? If you call this X, so if this is X, and this is y, and then we can just label this as z, right? So indirectly, what are they asking you? They're asking you for dz dt. So they ask you for dz dt, right? Once you have this in mind, it becomes easy. What equation can I write that will help me compute dz dt? Very clearly, you need to start by writing Pythagoras theorem. All right, you need Pythagoras theorem, and if you write Pythagoras theorem, the next you need to think of is applying your chain rule. All right, let's jump to the solution. All right, just give me 1 second. All right, sorry about that. So you notice it. This is the same diagram that I was showing you. So if you label this as x, y, and we call this z, we've been given some important information. They gave us the speed at which A is approaching that intersection. So dx dt, it was 90 kilometers per hour. But look at this. I introduced a negative sign there, similar to for dy dt, which they gave us as 100 kilometers per hour. It's also negative. Look at the explanation here. I said negative because x and y are decreasing. It makes sense, right? The intersection is not moving, but A is getting closer and closer to the intersection. B is getting closer and closer to the intersection. Do you see that that distance x is getting smaller? The distance y is also getting smaller as we head towards the intersection. By the time they hit the intersection, x and y will just be zero. You see, they're getting smaller and smaller. Therefore, the change in x with respect to time has to be negative. All right. And if you have that in mind, you know that you're looking for dz dt. What equation do I need? Pythagoras theorem. Differentiate using chain rule. You're going to have 2z dz dt, 2x dx dt, 2y dy dt. Just make dz dt the subject. So divide all through by 2z. All right. And you notice it, the only unknown that because we know what this is, you know what dy dt is. Do you know what x is? Yes, they told you was 60. You know what y is? Yes, y, they give you y as 80. And then do you know what z is? Yes, we can get it from Pythagoras. So now this is something I need to explain again. They gave you x as 60, and then they gave you y as 80. Obviously, from Pythagoras, you get that z is 100, all right? But be careful, these are meters. Meters, not kilometers. Not kilometers. I told you guys that the rate that you're giving should give you a reference point to what the other units are supposed to be. Look here, you're dealing with kilometers per hour. But look at this, it's giving us meters. You must always do the check. Because it's 60 meters, you need to convert each of these to kilometers. So 60 meters, you divide by what? 1,000. Remember, 1,000 meters equals to 1 kilometers. Therefore, 60 is what? 0.06. 80 here would just be 0.08. And here you just have 0.1. There you go. If you plug that in there, notice it, you get minus 134 kilometers per hour. All right. You can't plug 60, 80 and hope that your finance will be in kilometers per hour. It doesn't work. You must convert them to kilometers before you can use them. All right. And in summary, we say the cars are approaching each other at the rate of 134 kilometers per hour. All right. Is there any question before we jump to our last example? Ask your questions. Or do you want me to finish before you ask a question? Then I'm going to do so. But please don't ask me a question that I gave you as an assignment, by the way. So I know some of you so funny, right? So be careful of the kind of question you ask me. Because if you ask me a question from an assignment, you honestly declaration, you're breaking the rules. Because I say don't ask anyone, including even me, for help regarding your assessment. All right, let's look at this last one. All right. The last one, they say a man walks along a straight path at a speed of 1.5 meters per second. Okay, so let's assume the straight path is just something that looks like this, right? The guy is walking. So let's say that's our person. And you can choose your direction to be in this other side. I'll just assume that it's going that side. It's fine. You can choose it to be in the opposite direction. It's fine. In this case, it's not going to change your answer. They say a searchlight is located on the ground 6 meters from the path. So do you agree that 6 meters from the path? So the light is somewhere there, and the distance between that searchlight and the path, so this distance here is 6 meters. All right. And then they tell you that it's kept focused on the man. So the searchlight is always kept focused on the man. So it means that that light there is always kept focused at the man. So we're going to have something that looks like this. All right. So keep in mind that this distance here is going to be at the right angle. They say, at what rate is the searchlight rotated? Do you agree that when this guy is somewhere here, so let's assume that this guy moves all the way here. Now, because the searchlight needs to stay focused at the guy, you're going to have something that looks like this. You see that? And because of that, you're going to have some angle of rotation there. So we can call this theta. All right. So let's see how we can tackle this problem. Let's look at the memo quickly. All right. So if you look at it, that is my searchlight. It's always focused at the guy. We know why this angle is theta, because when that guy moves towards this point here, the light still need to remain on the guy, means it's going to be moving in that direction. That angle, the theta, is going to cover an angle, the theta, all right? They gave us 6 meters. So what information did they give us to start with? They gave us dx dt. The reason why I'm trying not to get anyone confused is positive 1, right? It's positive 1.5 because, like I said, it's just because of my reference that I'm using. All right, it's a reference I'm using. Another student can choose to say that this person was instead moving in that direction and the searchlight is somewhere there. So another person can instead draw it like this. And if you have this in mind, you agree that you might be tempted to say, okay, now move in the opposite direction from sir, which is not the case. All right, so we stick to it being positive, meaning that it can be moving from the left or the right. You see, when the question is ambiguous like this, where I didn't force you to say, oh, this guy is moving west or east, then you stick to positive. All right. And then what are you asking? We asking you for d theta dt when x is equals to 8. All right. Notice it, this distance 6 will not change. But now I've given you x is 8. From Pythagoras, you can compute the distance between that that light source and the person. It will just be 10. All right. What equation, again, you see, I go back to that equation. What equation can I write that will help me compute d theta dt? It means that equation needs to contain theta, right? And there you can see it's just trick. It's just tan theta. Easy. Tan theta is opposite over adjacent. There we go. So tan theta is x over 6. Therefore, if I make x the subject, I have x equals to 6 tan theta. Apply chain rule. So dx dt becomes, remember, derivative of tan is sec squared, so you have 6 sec squared times d theta dt. If you make d theta dt the subject, you just have, in this case, you have to divide dx dt over 6 cos squared. So 1 over cos squared is just cos squared. I don't know if you guys understand where this is coming from. So if you take 1 over sec squared, indirectly you just have cos squared, because sec squared by definition is 1 over cos squared. So if you say 1 over cos squared, it's just cos squared, all right? That's what we have, cos squared over 6. And we're just going to leave it as cos squared. We have 1 over 6 times cos squared. We know what dx dt is 1.5. Now, what do I do with this cos squared theta? You go to this diagram here. What is cos? Cos is adjacent over hypotenuse, so 6 over 10. So where you see cos squared, you just put 6 over 10 squared. There you go. And you have your answer, 0.09. All right. And the unit there you can see is rad per second. Remember, theta is the angle. So angle is measured in radians. Remember when you started with 1A, they told you we no longer use degrees. So don't tell me degrees per second, say rad per second. All right. So the Tesla is rotating at the rate of 0.09 rad per second. It's as easy as that. All right. Now, ask your question. Are there any questions?